The next in the series is to learn how to name acids. In the naming of acids, what will happen is you'll have a compound like HCl, and what will happen is you'll look at it and you'll see, hey, this is going to be ionic because it's got something that acts like a cation, something that acts like an anion. So you'll go ahead and you'll start to draw your scale like you should for any ionic. On the left, you'll have your cation at a +1, and on your right, you'll have your anion at a -1. But before you get any further, I hope you catch yourself. Anytime you have hydrogen by itself, only hydrogens on the left side of a scale, you have to just remind yourself, stop, I'm not doing ionics anymore. I'm now going to use the acid naming system. So what is the acid naming system? The acid naming system depends on what your anion is. If there are no oxygens in your anion, then you use a naming system that involves the prefix hydro. So this is hydro because there are no oxygens in the anion. And then chloric, CHLOR, and we don't do hydrochlorine. That prefix is changed to hydrochloric. And ic is indicative of the acid end. So cleaning that up a little bit, the name would look like hydrochloric acid. Let's do one more example that would use the hydro prefix. Suppose you had hydrogen together with fluorine. Excuse me. Hydrogen together with fluorine. You'd go ahead and make yourself a scale. On the left-hand side of the scale would be a hydrogen +1. On the right-hand side of the scale would be a fluorine -1. You're almost ready to use the ionic naming system until you remember, hydrogens only on the left, so I have to use the acid naming system. And since there are no oxygens over here, no oxygens means that we're going to use the hydro prefix, HYDRO, and then we would use fluorine, FLUORINE, but we changed that name to IC, hydrofluoric. So that would be the name of this compound, this acid, hydrofluoric acid. So let's see now, though, what happens when we start to make our ionic scales. And we put our H on the left because, again, it has a +1 cation. And we found our NO3 is our polyatomic anion, and it's a -1. We tell this by looking at our oxidation sheet. And if you look down at your oxidation sheet, you'll see NO3 -1 is nitrate. So what happens here, because there is an oxygen, once again we recognize, hey, no, nothing else besides hydrogen, so I need to use my acid naming system. But now there is oxygen present. And if there's oxygen present, we do not use the hydro prefix. We use the name of the anion, which is nitrate. So you look on your sheet, make sure you're looking at the one that says nitrate, and then the ending changes from 8 to ic. So this becomes nitric acid. No hydro out front, though. No hydronitric acid. No hydro out front because there's no oxygen. There is oxygen in the anion. The presence of oxygen means no hydro prefix. Similar example on this side of the board, we would be making our scales. We'd be putting in our hydrogen as our positive cation. We'd be putting in our NO2 -1. We'd look on our sheet and we discover this is called the nitrite ion. Make sure you can see the difference between nitrate and nitrite on your sheet. And so now we're just about ready to use the ionic naming system, but we recognize, there's only hydrogens over here. I have to use my acid naming system. But since there is oxygen in here, we're going to go ahead and make sure we don't use the hydro prefix. We use the nitrite name, but the nitrite doesn't, ITE is crossed off, and instead it changes it to OUS. So this becomes nitrous acid, NITROUS, nitrous acid. So in summary, for this particular section where there is oxygens present, if the ending of your anion is 8, you change to ick. And the way I remember that is I ate something I didn't like, ick. And if the ending is ite, I-T-E, then it changes to O-U-S. No way to remember that in a tricky way, but just one changes to ick and the other to S. And if I memorize the 8 one, then I know where the ite one goes. Okay, let's apply these rules to a couple of examples. First of all, we'll go ahead and try H3BO3. So we look at it, we think it's ionic. We start with our scale. We put a hydrogen on the left-hand side. We put another hydrogen on the left-hand side, and we put another hydrogen on the left-hand side. The 3 telling us there's 3 on the left-hand side. Then BO3 going on the right-hand side. Looking on my oxidation sheet, I see this is a -3 charge, and it has the name of borate. So I'm just about ready to use the ionic naming system until I see, hey, nothing but hydrogens on the left, so I know I need to use my acid naming system. There is oxygen here, so I'm not going to use the prefix hydro. So I'm going to write down the name of the anion, BROR, borate. But I remember that in my naming system, the 8s changes to X, and the name of this is boric acid. Another example, we'll go ahead and do AsO3 with some hydrogens with that. So H3, AsO3, again thinking that it is ionic, I would make my scales. You would have a hydrogen here, another hydrogen here, and another hydrogen here, totaling up to +3, because on this side we have the AsO3 polyatomic ion, which has the name arsenite, -3. Once again, once we get ready to do ionic naming system, we recognize nothing else but hydrogens, so we switch our mind to the acid naming system. There is an oxygen present, so that means we don't use the hydro. We write down the name of the RARSENITE, the arsenite ion. And then this ITE gets changed to OUS, and this is arsenous acid. Our next example, HBr, starts off thinking we're ionic. We notice, hey, nothing but hydrogens, so we're going to go to our naming system. And this time there is no oxygens over here, so we are going to use our hydro prefix, HYDRO, then bromine, but instead of the INE, we're going to use that to the ick. So this is HYDRO, BROMIC, hydrobromic acid. One final example, H2CO3, H2CO3, we go ahead and make our scale, thinking we're ionic. Hydrogen's on the left, 2 of them because of the formula. Only one CO3 on the right. It has a charge of -2. We notice its name is carbonate. Carbonate is that ion. So then we get ready, but we notice, hey, no anything but hydrogens. We might want to do hydro, but we notice the presence of oxygen, so we aren't going to use the hydro. We're just going to write carbonate. And of course, we ate something we didn't like, and it made it ek. So this is carbonic acid. And it's the acid that you might find in a soda pop that gives it that special little fizzy, stingy taste in your mouth, carbonic acid.